Okay.
Also shorten for
And thank
all right, so thank you, Tommaso, for agreeing to give the talk, and looking forward to hearing about the applications of neutral atom analog quantum computing.
So thank you so much. Can you hear me? Is it working? Yes. So thank you so much to the organizers, Kate and Hossein, for the opportunity to be here again. I spent a beautiful year a couple of years ago as part of my sabbatical, and I had the opportunity to interact with many of the people that are also here in the audience. And since then, I then joined Quera Computing, and initially more in a sort of senior scientist role, and now I'm really talking to very many people, both academics, commercial organizations, even governments, to start to give much more visibility to the activities that we do within the company. So today, of course, I will go back a little bit to my role of a scientist. I want to show some applications of our current machine that is available on a public cloud. And of course, give you also some hints of the directions that we are trying to pursue at Quera in the field of digital quantum computing. So let me give you a brief overview of the company. So we are based in Boston. I will be happy to take some of you later to a lab tour at Quera. We are right now more than 50, about 70 or 80 already in total between scientists, engineers that come from really top institutions all around the world. We have a working analog quantum computer on a public cloud. We work closely with AWS Bracket, which is the service from AWS providing access to quantum computing devices. And our mission is to build and commercialize a large scale, which means with a large number of qubits, and error-corrected digital quantum computers. We already work with many organizations, and we have hundreds of users that access our systems regularly. And for the younger generations, as well as for the colleagues of yours that are interested, we have plenty of open positions. I think that today we just updated the career web page on our site, so please feel free to have a look. And if you see any interesting positions through, among scientific, both in software, in hardware and applications, as well in engineering, feel free to reach out to us. As a company, we operate as a full stack with a full stack approach, meaning that not only do we basically build hardware based on these neutral atom, based on neutral atoms, but we also basically develop the software that is necessary to run applications on the computer, as well as to emulate the behavior of small quantum systems. This software is called Blockade. It's available on Julia and Python. And this is part of the efforts towards analog quantum computing, but we are also now working to upgrade all the software stack in order to accommodate the needs of digital quantum computation. And finally, we have a very strong team developing algorithms and applications across a wide spectrum of classes of problems, including combinatorial optimization, machine learning, and quantum simulation. And I would like to speak a little bit more about a specific application on quantum machine learning later on during my presentation. Of course, if you have questions, feel free to interrupt. As a company, we were founded back in 2019 as a spin-off of Harvard and MIT. And we closely follow the scientific breakthroughs of these two institutions. And since November 2022, we are going to complete 2 years in a few days. We have a working neutral atom computer that works in the so-called analog mode. I will explain a little bit more in a few minutes. With 256 qubits that is connected to the cloud from AWS. And since then, essentially also actually even before, we are also accompanying very closely the breakthroughs at Harvard and our collaborators at Harvard and MIT to basically develop our digital quantum computing capabilities, both by boosting the fidelity of both single and 2 qubit operations, as well as the execution of complex algorithms, also in the spirit of working with logical qubits, not only with physical qubits. So let me explain very briefly how these two modalities of computation actually work. And everything, at the end of the day, boils down to atomic physics and the way in which we sort of encode the qubit basis states into the internal levels of our favorite atomic species, which is rubidium-87. So if we focus on two specific states, like for example an hyperfine state and an excited Rydberg state, we can essentially encode our computation into an atomic register, which is essentially an ensemble of rubidium atoms, and then perform a continuous time evolution with a specific Hamiltonian, which is a native Hamiltonian for this system. I will show it in a few seconds. And then by employing certain specific capabilities of this computing device, namely the possibility of playing both with the pulses that control the intrinsic dynamics of the system, as well as the geometry of our atomic array, we can create interesting configurations such as this square lattice or this Kagome lattice, as well as this map of the world. Or by superimposing different snapshots, we can write the first hello world with an analog quantum computer. And the other modality is based instead on a different encoding of the qubit basis states, namely on the two hyperfine states of our rubidium atoms. But we still, of course, exploit the strong interaction coming from the coupling to a Rydberg state to basically produce or to execute our two qubit or multi-qubit operations. And basically here, the idea is that we have instead, we still start from a qubit register, and then we create different layers of either single qubit or multi or two qubit operations in a sort of discretized way. So that's one of the major differences between the so-called analog and digital modality of computation. There are, of course, many other subtleties. I'm happy to discuss them perhaps after the presentation. So let's go a little bit more into the details of the analog quantum computing modality. So the intrinsic Hamiltonian is actually very well known to the community. Also in sort of as a sense of acknowledgement to the work that I've done since the time I was a postdoc with Thomas back in Dresden. We were studying these things quite a lot. The Hamiltonian is made of essentially three different terms. One, the last piece, which is an interaction term between spins or atoms located at positions I and j on this lattice. This interaction strength specifically for the encoding that we choose is a van der Waals interaction scaling like 1/r⁶. And then we have an additional term, this intermediate term proportional to a parameter called the tuning that we can choose to be either global, so to be the same value for all the sites in our atomic array, or even local. And this is one of the latest features that we included in our offering through the cloud. And that's quite important also in the execution of certain types of applications I will be talking about later. And finally, this first term here that couples this hyperfine state to a Rydberg state is very relevant because it makes the system truly quantum, because it does not commute with the other two terms of the Hamiltonian. It is proportional to a parameter called Rabi frequency, and that we can control together with its phase. Now, once we clarify what are the roles of each individual terms of this Hamiltonian, we also can acknowledge the fact that we can really play with the tools coming from the fact that we can control very precisely the shape of these pulses, of all these three terms, the omega, the phase, and the tuning, by for example, creating these rectangular pulses that can certainly be used to implement gates in principle, but more practical even for certain specific combinatorial optimization problems, for example, that can be used to implement QAOA type of applications. The second shape, which is a sort of more regular pulse, can be used to simulate, for example, annealing or quasi-adiabatic dynamics. But we really have the freedom to explore a very sort of fuzzy pulses that can induce very highly non-adiabatic or very far from equilibrium type of dynamics. And on top of that, let's keep in mind that we, of course, can work with the very generic type of atomic arrays. So all of this, as I said, started this adventure in terms of exploring applications and the usage of our quantum computer at Quera started back in November 2022. I would also like to highlight that whereas I think from the atomic physics perspective and from the sort of scientific point of view, the physics in a way has been already known for quite a few years, and that's why I was also mentioned that I've been working on these systems several years ago. It's really a very strong, a very important also engineering effort to put, to transform or to create essentially a service for a broad community, not only of scientists, but also of practitioners, if you want, of quantum computing that would like to access this system essentially in essentially real time. And many of you, some of you at least in the audience, have been testing this machine over the past few months. So in the last couple of years, we increased the availability of this machine from 10 to more than 100 hours, actually 130 hours a week. And basically, we allow people from all time zones in the world to access essentially in real time our device. This machine has been also recently upgraded. We included some new features, for example, the local detuning that I was mentioning before. But we also increased the flexibility of the arrangements of our atomic cubic arrays, in particular by tightening the row spacing from 4 to 2 micrometers, and even including larger heights from 75 to 100 micrometers. And this gives the possibility to have essentially first a programmable disorder, or to create more advanced type of initial states that can be useful for certain applications, but also to enable different types of exotic lattices or larger system sizes for 1D or quasi-1D problems. On top of that, I just want to mention that I will not be speaking about our digital capabilities, although these are really an integral part of our technological roadmap over the next few years. But these are really important to explore several sort of types of applications. I'm mentioning here material chemistry, condensed matter system simulations, just to remain the space of scientific type applications. And all of these digital quantum simulation efforts are also driven by certain specific capabilities of our quantum computers. For example, the possibility of really shuttling the atoms around the simulation region that enables essentially long-range connectivity that would be, on the other hand, quite more difficult, substantially more difficult in the context of just the pure analog simulation. And one of the reasons is that the coherence time of these systems is greatly increased with respect to the coherence that we would get from just by coupling a ground and a Rydberg state and doing an analog simulation. The other big goals that we would like to achieve, of course, is the early demonstrations of error-corrected algorithms, and this is done in collaboration with many academic partners, and I would be happy to talk about that either now, but for those that will join me in the tour of Quera, there will be plenty of time to explore all these questions. Okay, then you have a question?
For the sort of cloud access, can you mix and match these two paradigms of programming things?
In principle, whenever we will, as soon as we will have the second machine on the cloud, on a public cloud, which will be the digital one, in principle you could do it either by basically having machines that would be sort of located in the same place, let's say co-located next to an HPC center, for example, or even on the cloud. In principle, if you could do that, you could run in principle what we call dual mode jobs. You could have part of the computation running on an analog device, the other part on a digital device.
These are actually
but not necessarily.
Yeah.
Yeah, we decided that these are actually quite different type of efforts. From the atomic physics perspective, in principle, you could even imagine to create a single device that incorporates both capabilities. It would be actually extremely interesting. The feeling is that it would require much more effort for perhaps a limited number of use cases, both scientifically as well as from the perspective of the applications. But that's a very good question. This is something that, of course, we have thought about quite in depth. Good. So let me, Thomas, you have a question? Yes.
So when you, for example, when you talk about the shuttling,
Yeah.
so that's something that's happening in the background, so it's nothing that one can directly access.
That's a good question. This is a part, of course, of the capabilities that we might be interested in, also in opening to the potential users. And this is actually quite important as soon as you would like to sort of compile a specific algorithm. No? Suppose that you start from, let's say, digital simulation of a condensed matter system. You want to create a circuit, but then from that circuit, you can compile that circuit in many different ways. No? So you have moves of your atoms, and you have specific set of native gates that you can play with. And the specific compilation can give rise to also to different, for example, runtimes of the same algorithm within the same machine, right? So this actually is very important effort that you can that we are of course we have been working with, not only in terms of developing, if you want, the hardware specs, but also to improve the software compilation stack. And this is actually something very, very important. And we are doing this also with very top-notch software developers, both on the scientific side and on the engineering side. So all these questions are very, very relevant to the development of the technology. Let me move a little bit in the direction of the applications. So of course, I want to highlight that I will be focusing only on applications on our Aquila device. So if you're interested in talking more about the digital capabilities and applications, I'm happy to take questions after the talk. And in particular, we are sort of focusing on three different classes of problems. One more on machine learning or quantum machine learning applications, both for classification of images, for example, or certain types of data that requires either binary or multi-class classification, as well as the regression and prediction of time series analysis. And we designed an algorithm together with our collaborators in Susanne's group. We mentioned the paper in a minute. That is based on a specific algorithm called quantum reservoir computing that generalizes a well-known classical algorithm that is called just simply reservoir computing. Another class of problems that we are focusing on are combinatorial optimization. And here I just want to mention that there is a set of native combinatorial problems that goes under the name of maximum independent set, that basically maps to one the number of variables in the mathematical problem or in the maximum independent set mathematical problem into the number of qubits of our device. But there are other non-native problems, like, for example, the famous QUBO problems, the quadratic unconstrained binary optimization, that while they do not represent a set of native problems that can be studied within our platform, there are methods, specifically these gadget methods, that allow us to encode these complex or complicated mathematical problems into a problem that can be sort of digested and executed on our device. I just also want to highlight, without really mentioning the word quantum advantage in any case, that even though we are not really reaching that limit by executing with the goal of solving this type of problems in our device, nevertheless, many of the interesting use cases that show up in the space of combinatorial optimization are also sort of suggested by conversations that we have not only with scientists but also with commercial organizations in logistics, in finance, drug design, and so on and so forth. So it's actually quite interesting to understand how these technologies actually closing the gap between very separate fields, very distant fields in principle. And finally, let me mention, of course, our efforts in the space of quantum simulation that is really inspired by initial ideas of Richard Feynman to simulate complex quantum mechanical systems with very highly tunable other quantum systems that we can control within a lab environment. And these are really problems that are inspired by, essentially by scientists. For example, the study of equilibrium, non-equilibrium phases of matter, but also the investigation of fundamental problems in physics, such as the study of lattice gauge theories. If I have time, I wanted to show an application that I essentially co-developed together with a colleague of mine during the period I was actually here at the ITAMP. But first, I would like to focus on in a specific application on quantum machine learning, and just emphasizing that if you want to have a better overview of all these applications, how they can be mapped into our Aquila device, please feel free to have a look at this paper from last year. So I will focus a little bit on the motivation of why we would like to start to study these quantum machine learning algorithms, then focus on the current available quantum algorithms, quantum machine learning algorithms and their limitations, and then discuss a bit about our approach, the quantum reservoir learning, and eventually conclude with some results. As anticipated, this work was done by a number of people at QuEra, including led by our colleagues Milan, Fangli, and Shentao, but also in collaboration with Onguier from Suzanne's group and, of course, Suzanne herself. And this is the reference of the paper that we put on the archive in July of this year. So regarding machine learning, I don't think I really need to justify why it is so important in our already daily life, I would say. So it's an integral part of our, digital investigations, for example, by the use of a product like ChatGPT, but it's of course very important for autonomous or self-driving cars, or even in the solution of problems such as the game of Go. And of course, as we all heard a few days ago, these efforts were acknowledged by the two Nobel Prizes, both in physics as well as in chemistry. So it's really a very important field that we cannot neglect anymore, even as physicists, of course. But now, as of today, we also have access to new types of data that are sort of generated by the use of machines like the ones that we are working on at QuEra, like our quantum computers. And therefore, a sort of natural direction for the field is the exploration of new types of algorithms that can really try to sort of classify or predict based on the input of these by this new data that can serve as input of these new types of algorithms. And in particular, we would like to understand whether there is any prospect for advantage in using such algorithms to both treat classical or quantum data, and in particular to use new types of algorithms, especially quantum algorithms, to treat these systems. An example of these efforts was sort of advertised or presented in this work by Google, by the Google Quantum AI team a couple of years ago, where they investigated basically the reliability or the efficiency or the accuracy of quantum machine learning algorithm to learn some features of quantum dynamics, of the quantum dynamics generated within their Google Sycamore processor. And until actually our results, this was the largest useful demonstration of quantum machine learning with up to 40 qubits. And I will show actually that we can go much more to much larger system sizes with our approach. This is an example of what we would call explicit demonstration or explicit usage of quantum data, but there are much more sort of convoluted approaches or convoluted data or implicit data that can even rise from the analysis of probability distributions in sort of psycholinguistic investigations done by some researchers, where they showed that by rephrasing problems that are proper of the field of linguistics in terms of what is called contextuality in the field of foundations of quantum mechanics, you can observe interesting violations of Bell-type inequalities. So one potential direction for the application of these new methods is even in fields that are in principle very far from physics. And if you're interested, I'm happy to discuss about those a little bit after the presentation. But actually, the question, as scientists are mostly as physicists, there is also some chemists. Luca, I learned that you are a chemist. I apologize if I'm focusing on another part of the audience. Of course, there are many interesting potential directions for exploration of this technology or these algorithms for the study of data that come from analysis of materials, or potentially even for the design of new types of drugs. And now, what about the algorithms that are currently available to us? So most of them are what we call variational quantum machine learning algorithms, where basically the idea is to replace the hidden nodes of a standard neural network with variational circuits whose weights can be sort of updated by implementing different versions of gradient descents or backpropagation and so on and so forth. The major, I would say, limitations of these approaches is the fact that they are extremely costly, so not differently from the classical approaches, even for very limited system sizes, but also their trainability sort of shows intrinsic limitations because of the structure of this multi-dimensional parameter space that displays these so-called barren plateaus. And on top of that, we are dealing with noisy devices, which again might create inaccuracies due to the presence of the corruption due to noise. So here we are with relatively rare and small-scale demonstrations that display eventually very limited potential for an advantage. So to address at least parts of these issues, we propose a different type of approach that is based on this idea of quantum reservoir computing that basically generalizes a sort of simple idea that has been known for several years in classical machine learning, in the classical machine learning community, which is the one of classical reservoir computing, where we basically replace the inner layers of a deep neural network with just a simple reservoir that can be made of very different, in principle, physical systems. One of them is the use of just standard classical spin systems that undergo a dynamics that is regulated by an Hamiltonian that includes both interaction terms between the spins as well as potentially external magnetic fields around which the spins precess. So these methods have been applied to the study of chaotic classical dynamics and in standard dynamical systems, or for example in climate modeling for the study of precipitation rates on a day-to-day basis. The generalization to quantum is actually not that complicated, at least I would say at a very high level. The main idea is to replace that reservoir that we have seen in the previous slide with a quantum many-body system that in our case is just our atomic array, in which we encode the features or some of the features of either images or time series through different types of potential encodings. So one possibility is to encode the features into our global detuning pulses, or in the position of the atoms that will, of course, reflect in different interaction strengths between the qubits because the interaction is position dependent. And finally, also in the local detunings, which is actually the new features that we released on Aquila. After we do that, we perform essentially a quench dynamics, of course, exploiting the transverse field that gives really the quantum nature to the whole algorithm. And finally, we take many snapshots to measure basically either the local magnetization or higher order correlators of the magnetization. So we actually observed that by going beyond the second order, these two-body correlations of the magnetization, essentially the accuracy of the algorithm saturates. So we actually, for all practical purposes, we stopped at the second order. So the measurement of the correlation of Zi, Zj. And finally, we apply just a simple linear classical regression and either obtain either, depending on the application, we either make predictions of the initial image, or basically we do predictions of the time series that we have been analyzing. The advantages are related to the fact that we don't really need we don't have this overhead of these many measurements that are needed to upgrade the weights of the neural network. As I will show, this algorithm is also relatively noise resilient. It is scalable, and in principle, it allows us to study systems that are very difficult or intractable from the classical perspective, classical numerical perspective at least. So please.
I think I'm missing something because, so if I understand correctly, the middle point, the thing that you're saying is that you take your inputs and you map it onto some parameter of your Hamiltonian, and then
Right.
you let your system evolve some time t, and then you measure,
Right.
and then you do a classical regression. What encodes the solution of like whether it is a prediction problem or something else? Like, is it on the classical regression?
It depends on the data, first of all. So first of all, we need to select the data set, right? So I will show an example right now, the classification of handwritten digits, the famous MNIST data set.
But you do have to agree beforehand on the way how to encode, both on the read in and read out side.
Right. You have to choose. So these are different modalities, different
Right.
possibilities. You choose one. You pick one of the three, or you can then you can compare even the three different approaches. So and this is what I will show. So you can choose different encodings, and depending on the encoding, you have a certain type of accuracy.
Maybe I'll reserve my question after the example.
Okay.
It'll probably be easier. Sorry.
Okay. Absolutely. But if it's not clear, feel free to ask again, because otherwise we might result a little bit too complicated. So here I just wanted to show a sort of proof of concept by performing just simulations on blockade, and then I will show results, actual results on the machine. And what we see is that the accuracy increases as a function of the dimension of the downscaled images. In this case, we are using this NIST data set, which are handwritten digits from 0 to 9, so a multi-class classification. And the PCA dimension here actually is equivalent to the number of qubits or atoms that we need to use in our simulations in order to predict to classify these images. What we see is that the accuracy increases as the number of qubits increase, and it also sort of saturates, or basically we obtain the same type of accuracy with respect when we compare to standard classical neural network methods, in particular this 4-layer neural network that already sort of saturates the accuracy for the specific data that we are sort of considering for this example. So this is to say that even if we use like a 5-layer, 6-layer, or 10-layer, excellent. Yeah, thank you, Kaden. We would observe the same type of accuracy on the test data. The other important feature that we observe is that by increasing the number of samples, so basically by increasing the number of snapshots, the quality of the accuracy that we observe also increases. And in particular, it saturates to about 1,000 snapshots per data set. Please.
Yeah, one question about this comparison.
Here?
Have you tried also with this setting quantum variational classifiers?
I don't know. I don't.
What
Have you
exactly
tried?
do you mean?
Quantum neural networks, variational zero.
No,
I don't think so. No.
because it's very hard for the size of the system. There's no way to actually do this. I mean, there are no quantum computers
No,
at
but
that
I mean
size.
in simulation.
Yeah, but these
Yeah.
are kind of.
This
Goes
in
to
real
1,000 qubits, right? I mean, that's a little bit hard to do.
So first of all, the classical
100
neural
qubits,
network
sorry.
already, the classical neural network has thousands of parameters, right? So if you really want to do an apple-to-apple comparison, you should need a variational circuit that should be at least as complex as the classical one. But that's not the spirit. That's not the spirit of the
Yeah, but I mean, if you are using up to 20 features.
qubits. Yes.
That should be possible with.
But 20 features does not necessarily mean, in principle, that Okay, you could try with 20 variational parameters. That could be doable, right?
No, I mean, but for the inputs. I mean.
No, the input is correct, but then the question is how deep or how complex would you like to choose your variational circuit in order to produce, to have an accuracy which is already the best that you can get with those number of features. And that's the point here. So we choose a classical neural network to compare with that sort of saturates the accuracy that we would expect on those downscale data set. That's a sort of tricky thing. We can discuss about that later.
Sure.
I think that's an important point to make here.
Okay.
The other, now I want to move in the direction of showing data on the actual machine. So we first sort of restrict ourselves to a smaller problem, which is binary classification between digits 3 and 8, which is already complicated because in principle, even when you write, you could potentially confuse the digit 3 with digit 8. But what we interestingly see here is that when we're performing simulation, we're actually performing experiments on Aquila, we observe basically essentially the same type of accuracy. There is a small variation of 0.5% than what we observe on with the classical or the quantum reservoir computing, but in simulation. And this is actually an example of why I was saying in the previous couple of slides that this algorithm is actually quite very strongly noise resistant. The second basically a multi-class classification, a full set of data with all the digits from 0 to 9 shows basically an increase shows that we have to increase the number of snapshots in order to increase the accuracy. But we also see that basically the device closely follows the prediction obtained in simulation. Now, another type of data set, and here this is exactly different. Go ahead.
Sorry, I think going through the example, I was still a bit confused with exactly
Please.
how the machine does the classification. So, because the way that you do is you input the parameters, in this case on the displacement of the atoms, and then at the end you let it evolve and you measure.
Right.
Then how do you translate that into a classification of 3 and 8? I think I'm missing that step.
That's just a linear. It's just a linear classifier that is, I think, a single line in Python.
Oh, so basically you take
It's just a
1-point and 2-point correlation function.
right,
like that,
right, and that
make
we use those data to make the prediction either of the classification of this multi-class classification problem, or the time series example that I'm going to discuss in a second. So that's the goal. So the goal of the simulations at the end of the day actually is precisely the goal. Sorry, the experiments or the simulation is to extract these correlation functions.
But then should I just think of the dynamics as doing like a complex, chaotic
Yeah.
thing that
Yeah.
kind of jumbles things
Yeah,
apart
it scrambles
somehow
everything, yes.
they become separable in
Yeah.
this like linear classifier?
Yes, yes, yes. But the point is that you can do this as efficiently, at least, as the most advanced classical algorithms. Okay, so that's one of the ideas. We are not claiming a quantum advantage of any type in these particular examples, but that's one of the goals, at least, of demonstrating this type of algorithms. So the second set of examples, okay, 3 or 4 minutes.
Yeah, sure.
It's okay. Okay, it's 3 p.m. Is the analysis of time series, and here we take another sort of prototypical example, which is the so-called Santa Fe laser time series in the chaotic regime that displays some very nice, very sort of strange dynamical behavior. And the way we implement basically the encoding for this specific example is basically by sampling or interpolating the pulses in this sliding window in different points, and eventually the goal is basically to predict the n+1 point of this small time series. The implementation is done by global pulses. We then, of course, we switch on the transverse field, and eventually take measurements of single body and two body correlation functions of the local magnetization. Now, it is nice to see that the experiment reproduces pretty accurately the simulations that we do on Blockade. But also, quite interestingly, both the simulations and the experiment are able to basically reproduce this feature that corresponds to this dip in the laser intensity at this particular time around 1080. So this is quite peculiar, I would say, so quite unexpectedly to see these features in the correlation functions. If we go back and if we then move forward and look at the accuracy of this algorithm on the test outcomes, we really see that the dynamics is very well reproduced by both the simulations as well as the machine. And here I want to go back perhaps to one of the comments that you were making on the different ways of doing the encodings. And what we see is that when we try to compare those both in simulation as well as on the machine, actually the local detuning feature, which is the one that we recently introduced, performs much better than the position and the pulse encodings. And here this has to do with the specific sort of thermalization dynamics of the system after a certain amount of time that I would be happy to discuss a little bit more in detail if you are interested, as well as the position encoding that displays some interesting position fluctuation from shot to shot due to of the position of the atoms within the optical tweezer. So all of these results actually have inside, I would say, really a lot of interesting physics that allows us to interpret, to be much more interpretable than we would naively expect. Now, last example, perhaps, how do we scale up this algorithm to much larger system size? So, the example that we take, or the data set that we take, is the one coming from the so-called tomato leaves data set, where the whole goal is to classify whether these tomato leaves display any type of disease. So whether the leaf is an healthy leaf or whether the leaf has any type of disease. Now, the way we do it, we basically take these pictures, we downscale them, and then we encode the grayscale grayscale of these pixels into our position encoding by basically tuning the strength of the interactions between qubits on the vertical columns, which basically again reflects into the different positions of the qubit along the vertical direction. And so we basically scale up the algorithm from 9 qubits to up to 108 qubits. And these are typical samples after we basically run the dynamics. And what we observe is that we basically see a consistent scaling of the accuracy with increasing qubit number. And this outperforms some very simple linear support vector machine simulation and sort of tends asymptotically, I would say, to the accuracy obtained with just our reference simulation method, which is this 4-layer neural network algorithm. But most sort of surprisingly to us is the fact that this is really sort of the first big successful quantum machine learning algorithm to date after the example that I was showing a few slides ago by another performed on another type of platform. And so with this, I don't know, I think I don't have additional time. Maybe I will leave some time for questions, and then we head towards the coffee break. Of course, there are other interesting features. Feel free to stop by and we can discuss. Thank you so much for your attention.
Thanks, Tommaso. Question?
So for the analog quantum simulation, would actually be a way to introduce losses and to simulate open quantum systems?
Yeah, that's a very good point. So you mean in simulations or in simulating in the quantum computer itself?
In simulation, I guess.
In simulation, yes. We have the software that I advertised called Blockade as also a noisy, there is a noisy part. The quantum computer intrinsically has several sources of noise and losses, of course. And you can find all the classification of the noise sources.
Can you control it so that I could simulate an open quantum system?
That's a good point. I think that's not really the goal of this type of implementations. That's a good question, of course, from the scientific or if you want, from the proof of concept, proof of principle demonstrations, there are a few things that you can control, right? From the perspective of providing the service, that's a completely different business, right? Because, for example, what I was showing that in one of the previous slides where I said, look, guys, over the past 2 years, we increased certain types of capabilities. It's clear that 2 years ago we could have done that too, but it was not as controllable as you would like to have as a service to a broad range of potential users. But that's, of course, a nice question. And one of our approaches, and this is actually more as a comment and attempt also to increase the spectrum of collaborations, we are very open to receiving ideas and explore some of these directions depending on the interest of some specific user, especially academics, of course. Please.
Is there at least in principle, let's say a classical limit that you could compare to? For example, if say your model has insane decoherence and therefore everything is diagonal, I guess, or something like that.
I can mention an example for this specific reservoir computing. The reason, yes, in principle, you can recover the classical reservoir computing results.
So which limit is that?
And basically the number of spin components instead of working in spin 1 alpha. Of course, this is just a theoretical limit if you want, theoretical exercise. But if you go to larger n, where n is the number of components of the spin, you should recover the classical spin simulation. This is actually something that we compared with,
I see.
So that's a very important, very important benchmark of the quality of the simulations.
Great. So I think in the interest of time, let's have further discussion over the coffee break. Also, normally we'd give, we would have we just push back the coffee break a little bit, but since we have a boundary condition with the QR tours, maybe let's start again at, say, 3:17, something pretty good. So we'll be 2 minutes late.
Minus 10 seconds.
Yeah, 10 seconds. Thank you.